Okay, we're at section 21.7, entropy in thermodynamic systems. Let me minimize this so it doesn't interfere with the presentation. One of the things we haven't done yet is indicate how to evaluate entropy numerically and how to discuss entropy for a macroscopic system with a huge number of particles. Both of these were performed through statistical means by Boltzmann in the 1870s, and the numerical evaluation of the entropy appears in its current accepted form as S equals KB natural log of W, where the W stands for Wahrscheinlichkeit, the German word for probability. Now, I'm probably not pronouncing it that well, but that's what it is. The author uses the W for ways, the different ways um, uh, you can present something. So the the values, the units of entropy are those of Boltzmann's constant, joules per Kelvin. Um, so let's look at uh, an example. We have a large volume of gas in a container, and we can divide that volume into a lot of different volumes. So we'll find one molecule in this VM. So W is equal to V divided by VM. And if we have two different molecules that we want to locate, then W. Now this W is not work. This is uh, the ways, the number of ways that we can find it. So W equals to W squared, which is equal to V over VM squared. And if we have uh, N molecules, um, on the order of Avogadro's number, then it's V to the VM to the nth power, astronomical number. So SKB, S equals KB times the natural log of W, which is the KB times the natural log of V over VM uh, to the nth power, which is by uh, the laws of logarithms, N times KB, natural log of V to the VM, which ends up being NR to the natural log of V over VM, R being our gas constant that we're familiar with seeing. Okay, entropy and energy spreading. We can, if a basketball falls to the ground, it's going to bounce and bounce and bounce, and the initial potential energy is going to decrease, and it's going to increase the temperature of the air in the ball and the part of the surface of the ball and the surface of the floor around it. We wouldn't expect all of those energies to reconcentrate and make the ball bounce spontaneously. So entropy and energy spreading, the energy is spread, um, uh, you know, over time. Let's look at entropy change um, in in this boiling pot of water. ds is equal to dqr divided by T, temperature. So we know that S is equal to KB times the natural log of W. So the delta S is equal to the integral, initial to final of ds. Well, if ds is equal to dqr dt, the integral um, uh, then it's equal to the integral of the initial to final of dqr over t. And that's, so the delta S is equal to KB times the natural log of WF divided by W uh, I, the initial uh, over the final. Okay, let's look at an ideal gas is taken from an initial temperature Ti to a higher final temperature of Tf along two different reversible paths. Path A is at constant pressure. Path B is at constant volume. What is the relationship between the entropy changes of the gas for these paths? Well, it's A. Delta SA is greater than delta SB. QR is equal to uh, change in internal energy minus work. But for delta V equal zero, in other words, a constant volume, the work equals zero. And for constant pressure, uh, for, I mean, sorry, for delta, for the change in pressure equals 0, that means constant pressure, then W is negative for the expansion. So the delta SA is greater than the delta SB. Okay, I had to revise this slide. That's why you have this equation at the bottom. So delta S is equal to integral of initial to final of dQr T. Delta S is equal to Q hot over hot temperature minus Q cold over cold temperature. Um, and we know that from the efficiency that Q cold over Q hot is equal to the cold temperature over the hot temperature. So the delta S equals 0. Um, so for a reversible cyclic process, the the uh, the path integral dqr over t is equal to 0 for a reversible process. And we studied the reversible processes are idealizations. Okay, let's entropy change in a free expansion. When the membrane is ruptured, the gas will expand freely and irreversibly into the full volume. And there's no way that the gas, once that membrane is punctured, that the gas will return to the lower half. Work has to be done to get it. So delta S is equal to the um, uh, integral from initial to final of dqr over t. And since t is constant, we have 1 over t integral of the initial final of dqr, but the integral for uh, initial to final of dqr is equal to the negative w on the gas during the expansion, negative work. And so that's equal to nRT natural log of V initial over V final. So the delta S is equal to NR times the natural log of V final minus V initial. Now let's take a process where you have the a hot reservoir T hot and a cold reservoir T cold. So the delta S is equal to uh, Q over T cold plus the minus Q over T hot. And that's equal to Q over 1 over T cold minus 1 over T hot. And that's greater than 0. And that's the end of section 21.7. Okay.